Hello, good morning, good afternoon, everyone. Today, I'm going to talk about deep unfolding, a data-driven approach for signal processing. My name is Tadashi Wadayama. I'm a professor at Nagoya Institute of Technology. Before starting the lecture, I'd like to explain the outline of this lecture. Deep learning, as you know, is not only useful for training deep neural network, but it can also be applied to optimize the internal parameters of differential iterative algorithms. This approach is known as deep unfolding. This lecture provides an introduction to deep unfolding, especially focusing on sparse signal recovery algorithms. The main content of this lecture can be divided into 5 sections as follows. In the introduction, I will briefly explain the basic idea of deep unfolding. Then, the concept of differential programming will be introduced. In the section of deep unfolding for gradient descent, I'm going to talk about the details of deep unfolding by using a concrete example based on gradient descent algorithm. The section deep unfolding for TISTA is the main content of this lecture. You will see the benefit of deep unfolding in the sparse signal recovery tasks. The final section provides concluding remarks. Okay, let's start with introduction to a deep unfolding. You know, deep learning has shown huge success in various fields, such as large language model like ChatGPT, image generative model. There are many generative AIs nowadays, and convolution networks for image recognition. Deep neural networks are often treated as a black box trained using large dataset without explicitly incorporating prior knowledge or domain-specific insights. While deep neural networks perform very, very well on many tasks, they require large amount of labeled training data, and their trained parameters are difficult to interpret. So this is called interpretability problem. In contrast, there another approach. The mathematical model-based approach formulates the desired signal processing task as an optimization problem and selects an iterative algorithm to solve it. This approach can utilize domain knowledge, but may lack flexibility to adapt the environment. As mentioned, the lower part, although powerful, the black box approach requires a large amount of training data. This is a drawback of the neural network approach. And also, no domain knowledge can be used. Okay, is there any mixture of these two approaches? Yes, there is. Model-based deep learning techniques aim to incorporate learnable parameters or neural networks into mathematical models of the target system. This allows for flexibility in learning from training data while effectively utilizing domain-specific knowledge. This figure illustrates the concept of model-based deep learning. The model at the center has the internal trainable parameters, and internal neural networks. These internal parameters can be trained by using standard deep learning technique. Such a model requires a smaller amount of training data compared with the black box approach and illustrated at the left-hand side of this figure. Because the number of trainable parameter is so small, you see, in the case of black box approach, we need a neural network with many trainable parameters. Compared with that kind of big model, in the case of model-based deep learning, we only have to train the much smaller number of trainable parameters. You see, so at the bottom of the picture, you can see the requirement of the data is illustrated. So in case of a black box approach, we need lots of training data, but in case of model-based deep learning, we need a less number of trainable, data for training. Okay. Okay, so the advantage of the model-based deep learning can be summarized as follows. The first merit is effective utilization of domain knowledge and the mathematical model. So we can make use of what the previous researchers have developed. So this is kind of domain knowledge. In other words, we can stand on the shoulder of giants. The second merit is that it requires less training data. That's a very nice point. In the case of signal processing, the environment is rapidly changing. So fast real-time training is needed in many cases. Fast training is a strong point of this approach. Lastly, model-based deep learning often provides better interpretability of the learned results. It is widely recognized that it is not easy to interpret the learned results of deep neural networks. In the case of model-based deep learning, the training parameters have own specific role, and the learned results are relatively easy to interpret compared with the black box approach. This is another advantage of model-based deep learning. Okay, now I'd like to explain deep unfolding. Deep unfolding is a methodology for designing algorithm that applies model-based deep learning concept to iterative algorithms, aiming to create flexible, learnable algorithms by embedding learnable parameters into the algorithm's internal structure. The concept of deep unfolding is to apply deep learning techniques to iterative signal processing algorithms. By unfolding the processing of the iterative algorithm along the time direction, we obtain the neural network model similar to deep neural networks. So we can apply standard deep learning technique to train such trainable parameters embedded in the algorithms. That's a basic idea of deep unfolding. It's very simple. Okay, you see the figure. The left block diagram represents the process of an iterative algorithm. For example, gradient descent algorithm, or stochastic gradient descent, or TISTA, and so on. And this is the process of iterative algorithm. So you can see the algorithm contains sub-processes like sub-process A and sub-process B and sub-process C. And there is a loop structure in the algorithm. So this is an iterative algorithm. By unfolding this process along the time direction, we can get the multi-layer structure as shown on the left. As shown on the right. You see, now the sub-processes are sequentially ordered like subprocess A, B, C, A, B, C, A, B, C, and so on. So this graph, this network can be seen kind of neural network. Some trainable parameters can be embedded into the layers. Now the multi-layer structure looks like a multi-layer neural network. So such a neural network can be trained using standard deep learning techniques like mini batch learning, backpropagation, and SGD to adjust internal parameters based on the training data. Okay, the right figure presents the training process of deep unfolding. The output from the model and the supervised signal are fed into a loss function. A loss function measures the discrepancy between the supervised signal and model output. Okay, usually we can use the, for example, mean squared loss, mean squared error loss function, and cross entropy for classification problem. So there are many types of loss functions. By using the back propagation or automatic differentiation, we can get the gradient information of trainable parameters. This kind of gradient information is so important to update the internal trainable parameters. The gradient are then used for updating the trainable parameters in the model. For the parameter update, we can use any optimizer, such as stochastic gradient descent, SGD in short, and also momentum method and Adam method. There are many possibilities. Okay. Now I'd like to explain typical advantage of deep unfolding. Typical advantage obtained by deep unfolding is to improve the convergence speed of the base algorithm. This figure presents the typical convergence behavior of deep unfolded algorithm. The horizontal axis represents the number of iterations, and the vertical axis represents the error, like a mean squared error. So smaller is better. Therefore, a lower curve is failure in the performance. Okay? The red curve represents the performance of deep unfolding-based algorithm. Compared with the conventional algorithm, the deep unfolding-based algorithm needs significantly smaller number of iterations for achieving required performance. Such a convergence acceleration has been observed for many deep unfolding-based algorithms. Of course, this convergence acceleration is significant benefit of the deep unfolding because the convergence acceleration leads to a faster and power efficient algorithm in many signal processing tasks. Thus, this is the main advantage of deep unfolding. Okay, now let's discuss differential programming. This differential programming is a paradigm where complex programs can be differentiated end-to-end automatically, enabling gradient-based optimization of parameters. So this is the main concept of the differential program. You know, there are many neural network frameworks. Maybe you using that kind of neural network frameworks currently, such as TensorFlow, PyTorch, and JAX, and Julia with Flux. These neural network frameworks, provide powerful automatic differential mechanism that make coding for deep learning easier and simpler. We don't need to manually implement the backward computation for gradient calculation. And we can concentrate only on the forward computation. So with these frameworks, maybe the programming for deep learning would actually be a nightmare because we need to implement backward calculation for gradient computation by ourselves. That's a very difficult task and a very complex task. These frameworks are very nice, and they can be used not only to deep neural network, but also to differential algorithms. This is the differential programming. This is a quotation from the recent book, The Element of Differential Programming by Blondel and Rule. So I'd like to read the definition. Differential programming is a programming paradigm in which complex computer programs, including those with control flows and data structure, can be differentiated end-to-end automatically, enabling gradient-based optimization of parameters in the program. This means that deep learning techniques can be used not only for training deep neural networks, but also for optimizing internal parameters of differential algorithms with inputs and outputs. Okay. So this the concept is originally proposed by Jan LeCun and several people. Okay, now we'd like to look at a very simple example. The sine function, you know the sine function. The sine function can be represented by an infinite series in equation 1. This is just a Taylor expansion or Maclaurin expansion of sine function. By truncating this series, we have the truncated sine function defined in equation 2. The t sine of x is the truncated version of the sine function. So we can consider it as an approximation of the sine function. Okay, and this is implementation of truncated sine function in Julia programming language. You can see that the series is truncated until the degree equal to 8 in this case, because n is set to 8. As you see, this is a simple code with a loop structure to compute the value of t sine of x. And also, you can see that there is if-else structure in the code. And also, in the last line, you can see flux.gradient. This line means that the first order derivative of t sine of x is defined as d underscore t sine of x. Namely, the automatic differentiation mechanism in the flux package is invoked to calculate the first derivative of t sine of x. Okay, let's look at the plot of d t sine of x. The marker with x symbol represents the value of d t sine of x. The dashed curve represents the value of cosine of x. As you see, the difference between the cosine of x and the t sine of x is invisible. Very, very small difference. We cannot see that difference. This example indicates that the program computing the truncated sine function is now correctly differentiated to cosine like a function. This is an example that a program with a loop structure and if then else structure can be easily differentiated. So the scope of differential programming is very wide. Maybe it includes deep learning and also model-based deep learning and also deep unfolding as shown in this figure. Because all of them rely on the automatic differentiation mechanism. However, the target of differential programming is usually more application-oriented. Namely, differential program is expected to produce adjustable and flexible software for a given environment. Some people call this is a kind of software 2.0. On the other hand, main focus of deep unfolding is to draw to achieve 100% potential power from an iterative algorithm. That is the aim of the deep unfolding, so the scope might be different. Okay, now let's move on the deep unfolding for gradient descent. I'm going to talk about the details of detail of deep unfolding by using the concrete example. The gradient descent method is an iterative optimization method that finds stationary point of the objective function by iteratively computing the gradient descent step. We can apply deep unfolding to this process by making the step size trainable and using minimal training to optimize them. Okay, let's look at the details. Assume that we have the differentiable function f like this. F is the objective function to be minimized. And we want to solve the minimization problem in equation 3. So x is a real vector of length n. So our objective is to minimize f of x in the Euclidean n dimensional narrow space. Okay. So the gradient descent method is an iterative optimization method that finds stationary points of the objective function by iteratively computing the gradient descent step in equation 4. You know the stationary points is the points where number f is the gradient f. Gradient f equal to 0. These points are called stationary points. So gradient descent method is a method for finding that kind of stationary points. The actual iterative formula is given in equation 4. You see, xt represents the system's state. So xt plus 1 represents the system's state of time t plus 1. So that state is given by xt minus eta times gradient of f at the point xt. Eta is a real constant that is called the step size parameter. Okay. Okay, now we now study the least square problem defined by equation 5. So now this type of problem appears in many areas such as data science and wireless communication. So this is in the case of data science, this type of problem appears in linear regression. And also in the case of wireless communication, this type of problem appears in mime signal detection. So this is very ubiquitous problem. So our goal is to solve this minimization problem, least square problem here, by using the gradient descent. You see that y is a given vector of length n, a is matrix of size n by n, and also x is a vector of length n. Okay, let's derive the gradient descent step to solve the least squares problem. The gradient of the objective function is given by equation 6. You see, the gradient of the squared Euclidean distance between y and ax is given by a transpose times ax minus y. This is a well-known fact. Therefore, we have the gradient descent step for the least square problem in equation 7. So you see, this is a state evolution equation for the gradient descent method. So the gradient, we can put the gradient in equation 6 into the equation 7. We can get the gradient descent step for the least square problem. Now we can apply the idea of deep unfolding to this gradient descent step. Which parameters should be trainable? So you see, we make some parameters trainable in deep unfolding. Which parameter should be? One reasonable choice is to choose step size parameter eta as a trainable parameter. So in the following discussion, 8t is treated as a trainable parameter. You see, the step size eta t can be trained. Okay. So this gradient descent step can be regarded as a neural layer. If the iteration count t goes to up to L, we have L multi-layer network as shown in the figure. So you see, the above equation is the gradient descent step of this problem. And the middle figure in the dashed box is illustrated version of the gradient descent step. And this gradient descent step can be regarded as a layer, one layer of neural network. That's the idea of deep unfolding. Okay, and now let's look at the training process. The training process is shown in this figure. The supervised signal generated from the mini-batch generator and the output from the gradient descent iteration are entered to the loss function. At the right-hand side, you can see the loss function. Loss function get the input from the mini-batch generator. This is a supervised signal, and also loss function get the input from the output from this gradient descent algorithm. In this case, we use the mean squared error MSE loss function. The gradient is obtained by using automatic differentiation mechanism, and the gradient is used for updating the trainable step size parameters. So up below the loss function, you can see the back propagation. This part in this part, we can get the gradient information from the each stage. So that gradient information is passed to the optimizer, SGD or Adam and so on. And these optimizer updates the value of the step size parameters. This is the idea. This figure shows the detail of mini-batch training. A mini-batch generator sequentially generates bunch of mini-batches, like mini-batch 1, mini-batch 2, and so mini-batch n. For each mini-batch, trainable parameters are updated as previously explained. A mini-batch consists of set of pairs y and corresponding least square solution x opt. So in this case, problem is so simple. We can easily obtain the optimal solution by using the product of pseudo inverse of a times y. So this is the true solution of the this least square problem. So we can make use of this true solution as a training data. This slide shows the details of update of parameters. We here explain the simplest case, that is the SGD, stochastic gradient descent method. SGD is an iterative algorithm with n iterations. For each iteration, a mini-batch is first generated, and then the gradient vector is calculated. Finally, the trainable parameters are updated using the gradient information. There are many variants of SGD, such as momentum and Adam, and so on. We often use Adam for deep unfolding because Adam provides better results in many cases. This slide indicates the basic procedure for the SGD. So this is very similar to the gradient descent algorithm you see. And also in the case of deep unfolding, it is known that the incremental training is very effective for training iterative algorithm. The idea of the incremental training is illustrated in this figure. In incremental training, the number of iterations for gradient descent is gradually increased during the training. So this figure shows the basic idea. At first, we start with the gradient descent with only one iteration. And then we increase the maximum number of iterations by one. So in the second phase, we set the maximum number of iterations to 2. So we train the network with 2 layers. And then we gradually increase the number of layers. So that's the main idea of incremental training. So this incremental training is known and very effective in many cases. So we often use this type of training for deep unfolding. Okay. This is the implementation of deep unfolding based gradient descent in Julia programming language. The upper block includes the mini-batch generator, and the lower block contains the gradient descent method, including the trainable parameters, eta. So at the upper block, you can see this is a mini-batch generator. It returns y and x opt. Y is a vector of length n. This is randomly generated. And x opt is corresponding true solution of the least square problem. Okay, and you see there is the variable k. K represents the number size of mini-batch size, you see. The next block indicates the details of the gradient descent. X is initialized to 0 vector. And then you can see we have the gradient descent step, like x equal x minus eta k times a transpose times ax minus y. This is gradient descent step. So this is very simple implementation. Now we can see the training part of the gradient descent. This is the training code for gradient descent. You can see that very simple code is enough for incremental training. There are two loops. You can observe there are four loops, two loops. Sorry, two loops. There are two loops, outer loop and inner loop. The outer loop is used for controlling the number of iterations of gradient descent. The inner loop is used for actual training. The variable, you can see there is the variable GS. Variable GS includes the gradient information computed by the automatic differentiation mechanism. And GS is used also for the parameter update. The code is very simple. So in many cases, the deep unfolding requires this kind of training code. Very simple training code is enough for deep unfolding. Okay, let's look at the performance of gradient descent. The mean squared error is the average of squared error between model output. Model output means the output of gradient descent. Model output and the least square solution. Least square solution means the true solution of this least square problem. So the smaller is better. Smaller error is, we prefer smaller errors. Okay. And the horizontal axis represents the iteration count, number of iterations. And this figure shows the relationship mean squared error versus iteration count. The top curve, solid curve, correspond to the original gradient descent. We used optimal fixed step size parameter in terms of the convergence speed. So we used fixed eta for the top curve, but that parameter is optimal, you see. The lower two curves are the MSE of the deep unfolding based gradient descent. In this case, we use the periodic step size with period 2 and period 4. As you can see, the deep unfolding based gradient descent achieves significantly faster convergence. So, for example, at the iteration at the 50, the original GD reaches to the MSE 10 to the minus 3, but the DUGD and the accelerated gradient descent achieved two order magnitude better results. For example, DUGD achieves the MSE 10 to the minus 6 at the 50 iteration. So the speed of convergence is so different. So from this experimental result, there are several observations can be obtained. The first observation is that deep unfolding successfully improves the convergence speed of gradient descent. Very nice point. The second, in many cases, incremental training is beneficial. And third, only simple coding effort is needed to implement deep unfolding. Very simple to implement. Okay, now the next section focuses on deep unfolding for the iterative soft thresholding algorithm, ISTA. We call ISTA in the context of complex sensing. ISTA is a well-known algorithm for solving the last problem, which is a convex optimization problem for sparse signal recovery. Okay, we first introduced the problem setting of compressed sensing. Firstly, I'd like to show you our problem setting of compressed sensing. Let X be a sparse vector, which is the target vector. Sparse means that most of components in X is there. and only few fraction of the components in X is non-zero. This is called sparse vector. So X is a sparse vector. The observation vector Y is given by Y equals AX plus W. The matrix A is called the observation matrix or sensing matrix. The vector W is a noise vector. We here assume the Gaussian noise vector. The goal of the problem is to reconstruct X from Y as accurately as possible. This is our aim. The problem is also referred to as a sparse signal recovery problem. You see, the we get the Y, and also we know the sensing matrix A. So from the information of Y and A, we want to reconstruct X. This is our aim for sparse signal recovery algorithm. And also we know X is a sparse vector. So we have to use that kind of prior knowledge in the recovery process. The sparse signal reconstruction problem is formulated as a convex optimization problem in equation 9. This formulation is often called a last formulation. The first term of the objective function can be seen as the least square term, and the second term is an L1 regularization term that prefers a sparse solution. The parameter lambda is the regularization coefficient that adjusts the relative strength of the L1 regularization term. We can use any convex optimizers or convex optimization algorithm to solve this last problem. Among all convex optimization problem, TISTA is a very well-known iterative algorithm for solving the last problem. The iterative formula of TISTA is given in equation 10 and 11. The equation 10 is called gradient descent step, and equation 11 is called a shrinkage step. The shrinkage step involves the soft thresholding function defined in equation 12. The shape of the soft thresholding function is illustrated in the figure like this. In 2010, Gregor and Lucan proposed a trainable version of ISTA, which is called LISTA, learnable ISTA. The iterative formula of LISTA is given by equation 13 and 14. The gradient descent step 13 includes the matrices BT and ST. These matrices are trainable parameters. So BT and ST are tuned by using the deep learning technique. After appropriate training, LISTA converges significantly faster compared to the original ISTA. This research can be considered as a pioneering work in deep unfolding. So maybe this work can be considered as the start point of deep unfolding. This slide summarizes pros and cons of LISTA. Of course, LISTA is a very nice algorithm. The performance of LISTA is indeed good. It has a very fast convergence performance compared with the original ISTA. Very, very nice. But unfortunately, learning process is quite unstable, and training takes a long time because this includes many trainable parameters. You remember that we made matrix BT and ST trainable. So a matrix contains many trainable parameters. So this actually have the many trainable parameters. And also, hyperparameter tuning is critical. This suggests that there is a possibility uh, of developing a more easily trainable variant of ISTA. So we can think that Lister is not the final answer. Okay, this slide shows the idea of deep unfolded ISTA. Sometimes we call DU ISTA in short. That is a simpler version of learnable ISTA. The main feature of DU ISTA is that step size parameter and shrinkage parameters are trainable. So you see in the equation 15 and equation 16, you can see red variable eta t and mu t. And these parameters are considered as trainable parameters. Compared with the list, DU ISTA involves a significantly smaller number of trainable parameters. This leads to stable and fast training process, and less training data is needed. This is a notable strength of DU ISTA. This figure shows the relationship between the MSE and iteration count of DU ISTA. The horizontal axis represents the number of iterations, and the vertical axis represents the MSE. The upper curve indicates the MSE performance of the original ISTA. The lower curve corresponding to the MSE performance of the DU ISTA. We can observe that the DU ISTA achieves much smaller MSE than that of original ISTA. You see, there are ISTA is actually ISTA provides very slow convergence like this. Compared with such a slow convergence, proposed DU ISTA shows significantly faster convergence. This fast convergence behavior is a remarkable advantage of DU ISTA. Okay, this figure presents the trained parameters. So this means that after training, we get the trained result, trained parameters. This figure shows the trained parameters. The step size parameters and the shrinkage parameters. You can see that step size parameters are fluctuated up and down like this. We can see some zigzag pattern in the trained sequence. This variation of the step size parameters appears very important to accelerate the convergence of ISTA. Okay, next I'd like to show you a simple demonstration of sparse signal recovery process of the original ISTA and DU ISTA. Just a moment. Okay. This is the original ISTA case. You can see there is two figures. The left-hand side, left figure indicates the original sparse signal. And the right-hand side, this is the state of ISTA. So now I'd like to show you animation of reconstruction process. You can see at the top of the right figure, you can see the number 150, 190, 200, 230. This is the number of iteration of the ISTA. So now you see the reconstruction, the state of ISTA is becomes very similar to the original signal, although there are some noises around zero. You see, now we reached to iteration 750. Now the reconstruction becomes very nice. But we can see still some noisy signal around value zero. So now we reach it to 1,000 iterations. Okay, this is the reconstruction behavior of the original ISA. It works well, but the convergence is very, very slow. And then I'd like to show you the case of DU ISTA. This figure also shows the state evolution of the state vector of the DU ISTA. Here you see I equal to 0. This is an iteration count. Okay, let's start. 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 15, 18, 19. So you see, at the 19th iteration, we get almost the same signal as the original signal. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 19. So no noisy signal can be observed around zero in this case. So this animation indicates that the convergence of DU ISTA is so fast compared with the original ISTA. Okay, so now let's get back to the our slide. Okay, you have seen that deep unfolding successfully improves the speed of convergence of ISTA. You may have the question, why does convergence accelerate by using deep unfolding? This is actually very good question. One reason is that the learned step size provides small spectral radius of the linear iterative system. If we linearize the ISTA iterative system around the convergence point, we can get the approximate linear iterative system. This process is also called linearization around a fixed point. The convergence speed of the linear iterative system is dominated by the spectral radius of the system. A training process of the deep unfolding can automatically find a good step size sequence minimizing this spectral radius. Manually setting a step size to fully leverage these effects is extremely challenging. So, automatic adjustment by deep unfolding is a computationally tractable approach for controlling the spectral radius. Okay, now let's look at the one of the state-of-the-art sparse signal recovery algorithm. The name is trainable ISTA, we call TISTA in short. That was developed by Ito, Takabe, and me. The recursive formula of TISTA is shown from the equation 70 to equation 21. They looks very complicated, but the main structure is the same as the original ISTA. Equation 17 is the gradient descent step, and equation 18 is the shrinkage step. We made the step size parameter trainable. This is the reason why the algorithm is called trainable ISTA. This is the signal recovery performance of TISTA. The vertical axis represents the normalized MSE, and the horizontal axis represents the iteration count. Compared with the powerful known algorithms such as AMP and Lister, these are known powerful conventional algorithms for sparse signal recovery. TISTA provides significantly faster convergence speed. This result indicates that deep unfolding is a powerful method to construct a fast iterative algorithm. Okay, I'd like to conclude this lecture with several concluding remarks. In recent years, application of deep unfolding have been actively explored in various fields, such as wireless communication, image processing, linear control, and linear control. For example, in the wireless communication field, as we discussed, sparse signal recovery algorithm has been actively studied, and also MIME signal detection, MIME precoding, RYS signal processing, power action problem, and also error collection for LDPC codes. The deep unfolding idea is incorporated to improve these algorithms. There are many works have been published. And in the field of image processing, for example, in order to accelerate the process of making the picture, MRI image reconstruction is deep unfolding is applied to MRI image reconstruction and super resolution, and also some deep unfolding is applied to several phase retrieval algorithms. There are many applications have been proposed. Okay, in conclusion, deep unfolding is a promising methodologies that combines the strengths of model-based approach and deep learning. It offers several benefits such as convergence acceleration and effective utilization of domain knowledge, and it has a strong interpretability. So deep unfolding has been successfully applied to various signal processing tasks, including sparse signal recovery, MIME detection, and more. And actually, it is quite easy to apply deep unfolding to your own iterative algorithm. Please try to use this idea of deep unfolding for improving the performance of your algorithms. There are still some challenges and future directions for deep unfolding, such as need for fast real-time learning, validation with real data, and hardware-related considerations. These problems should be addressed in the near future. Okay, and this is the end of my lecture. I hope you enjoy the contents of this lecture. Thank you very much for watching this video. If you have any comments, questions, please feel free to send them to me. Thank you again. Goodbye.